Okay, we're going to record our last video here, which is the divergence theorem, section 13.9. I'm going to tell you a secret. I just did the whole video and it didn't record. So I'm redoing it now, and I'm going to apologize if I check back here and there to just check this screen and make sure that little red dot is over the screencastify button and that I am in fact recording, because that was a little bit disappointing. But anyways, the divergence theorem. So before I get too far ahead of myself, I'm going to refer you to page 828 in your book. It does a nice job of kind of summarizing a lot of these sections in chapter 13. There's a lot of formulas. And it can be a little bit overwhelming. And, even on page 828, they're not all there. But the basics are, and they do give you a nice visual to go with each of them, with, your Green's theorem, your Stokes theorem, and now your divergence theorem. So you might want to check that out. One of the hardest things I think in this chapter is all of the equations, and so many of them are equal, and it's hard to tell what you're supposed to be using. So even with the divergence theorem that I'm going to do here right now, remember flux is through a surface of a vector field, normal to the surface. Okay, and then even that we said, well, that's the same as this. Okay, and then if you remember even further, we said, well, when we want to evaluate that, let's do this. Okay, so there was a lot going on. Okay, and then once we add the divergence theorem, which is the fact that this flux is equal to a triple integral. Okay, so much like when we did Green's theorem, we went to a line integral to a double integral over an area. Now we're going from a surface integral to a triple integral over a volume for divergence theorem. So it kind of just knocks it up another dimension here for you. E is going to be that solid. Okay, and it's equivalent to the divergence of f x, y, z dv. Okay, so you can kind of think about it like, remember, like flux, we talked about how it's this vector field through a surface, and now we're doing the divergence through a volume. So you can kind of think about how it's like, your divergence is how much it's flowing, right? We kind of talked about that. Your divergence is like a flow through the volume. Okay, so definitely when you are doing this, try to go beyond just, which equation do I use? Let me fit the pegs in the holes and just do exactly what I'm supposed to do. It's not these aren't easy concepts, but do your best to try to get as much of it as you can and kind of think about, what am I actually going to be calculating here? And try, even if you're not right, sometimes you're like, oh, I think this is what it's doing. That's how your brain kind of develops that knowledge, that understanding of these. Just seek out more and more examples. Look on YouTube, look on Khan Academy, look on, read your book, look in a different book. Your textbook from last year, if you took, or I guess 2 years ago, if you took AB, has the same stuff in it. Grab one from my classroom or for somebody who's taking it, and try to look at a different perspective than just me and your textbook. But anyways, let's get back to this. Okay. So basically, this is your divergence theorem. Okay, we're only going to do 2 examples. This video won't be very long. The first one, we're just going to verify the divergence theorem. So it's exercise 2 in your book, which gives us f, so your vector field is x squared I plus xyj plus ck. Okay, so we need the field, right? And then we also need the solid. So E is a solid bounded by the paraboloid. Z equals 4 minus x squared minus y squared, and the xy plane. Okay, so we'll just quickly draw that. Paraboloid, right? Axis is the z-axis. The vertex is going to be at 4 on the z-axis. And then when we're in the xy plane, we would have z is 0, so we have a circle with a radius of 2. Okay, so roughly that's your shape to it. Okay, so that surface, the two things that we need here to do that left-hand side, right, are PQR. So we've got that PQR, and then G of XY, which is Z, which is 4 minus x squared minus y squared. Okay, so we would do your double integral of negative p, so negative, let me do dg dx would be negative 2x, and dg dy would be negative 2y. Okay, so negative p, so negative x squared times dg dx, which would be negative 2x. So we have a positive 2x cubed. Okay, minus q, so minus xy times dg dy, which is negative 2y. So we'd have positive 2xy squared. Okay, and then plus r. And then dA. Okay, and we definitely need to change some things out. The first thing being that we want this in polar probably, right? Or cylindrical coordinates. So we can describe that paraboloid where r would go from 0 to 2. Theta would be between 0 and 2 pi. And then z is dependent on r, right? Z anywhere from 0 to 4 minus x squared minus y squared. That's just 4 minus r squared, right? X squared, remember x squared plus y squared equals r squared when we're talking polar. Okay, so 4 minus r squared. There we go. Okay. And, you know what? We're not even going to need that yet, right? Because remember, D is just that in the xy plane. That's D. Okay. So we just really need the r and the theta. Okay, so we want to do the integral from 0 to 2 theta, integral from 0 to 2. And we got to convert all of these x's and y's. So we'd have 2r cubed cosine cubed theta plus 2r cubed cosine theta sine squared theta. And then z, remember z is 4 minus r squared. And then since we're switching from x's and y's, we got your r, dr d theta. Okay, and there is some simplification here that you might not see right away, but look at those first two terms. If I factor out a 2r cubed cosine, I'm left with cosine squared plus sine squared. So that's nice. Okay, and then make sure I distribute that r. So 2r to the 4th cosine theta plus 4r minus r cubed dr d theta. Okay, do this integral. So I'm going to have 2r to the 5th over 5 cosine theta plus 4r squared over 2 minus r to the 4th over 4, evaluated from r equals 0 to 2. So the 0 is not going to matter. I'll have 32. Let me just make sure here. Oh, I see what I did differently. Okay. Okay, I'm good. So 32, so 96 over 5 cosine theta. Right? Oh, not 96. So it would be 32 times 2, so 64. Okay, plus 8 minus 4. Okay, so I'm going to have the integral from 0 to 2 pi of 64 over 5 cosine theta plus 4. All right, so that's going to be 64 over 5 sine theta plus 4 theta from theta equals 0 to theta equals 2 pi. Everything's going to be 0 except for 4 theta when theta is 2 pi. So that's going to give me 8 pi. Okay, now we're going to verify the other side, which is, let's see here, that we can do the integral over the entire solid of the divergence of f, okay, and then dv. Okay, so your divergence of, well, and we've got the limits of integration that we figured out up here. Okay, so we can go from 0 to pi, 0 to 2, 0 to 4 minus r squared. And we're going to need a dz, and r, dz, dr, d theta. Okay, and then your divergence of f, remember your divergence of f would be df dx plus df dy plus df dz. Okay, and so you don't have to scroll back up. F was x squared xy z. So your divergence of f would be 2x plus x plus 1. So 3x plus 1. Okay, which 3r cosine theta plus 1. Okay, so we've got 3r cosine theta plus 1. All right, I'm going to check to make sure that I'm recording. Yay, I am. Okay. So this integral first. I'm going to, distribute the r. So it'd be 3r squared cosine theta plus r squared. Okay, when I integrate with respect to z, there's no z here. So it's just going to be 4 minus r squared times 3r squared cosine theta plus r. Okay, and then since next I wanted to integrate with respect to r, I'm going to expand that. So I'll have 12r squared cosine theta plus 4r minus 3r to the 4th cosine theta minus r cubed. Okay. So that will give me a 4r cubed cosine theta plus 2r squared minus 3/5 r to the 5th cosine theta minus r to the 4th over 4. From 0 to 2. Okay, so I'm going to have 32 cosine theta plus 8 minus 96/5 cosine theta minus 4. Okay, and I'm just going to, at 8 minus 4, I'm just going to do a real quick little plus 4. I shouldn't do that because that's not doing a good job of showing my work. I'm getting lazy, so I'm just going to rewrite it. And also glitchy, iPad. Thank you. I'm not going to combine the cosines because what's the integral of cosine? Sine. And when I plug in 0 and 2 pi, 0. So I'm not even going to take the work to do that. Okay, so I'm going to have 32 sine theta plus 96 over 5 sine theta plus 4 theta from theta equals 0 to theta equals 2 pi. And just like last time, the only thing that matters is 4 theta when theta is 2 pi, and I get 8 pi. Okay, yay. All right, so we're going to do one more example, okay? But that one, we verified that both sides of that Stokes theorem, the divergence theorem were equivalent for that particular problem, regardless of which side we chose to use or which one you might think is easier. Okay. Last one that we're going to do with this is, I believe, exercise number 12 in your book. Okay, so we have the vector field. There's a lot going on there. And we have S is a surface of a solid bounded by the cylinder x squared plus y squared equals 1, and the planes z equals x plus 2 and z equals 0. Okay, so now this is one where we cannot easily calculate this piece. Okay, we do have F, P, Q, and R. We got that. Okay, that's not so hard. It's the G, which has to be a function of x and y that describes z for the surface. And that's not going to work. Okay, we have a cylinder. Above the xy plane. And when we slice through this, let's see here, it kind of like be shaped like this guy here. Okay, like that plane comes through in the xz plane, it slices through. So up here, this would be when, let's see here, when x is 2, y is 0, and z is 4. Okay, and then somewhere in the middle, when x is 0 and y is 0 and z is 2. And then over here, when x is 0, oh, did I get that right? When x is 0, y is, oh, I guess it comes out, let's see here. When x is negative 2, when x is negative 2, yeah, it slices through kind of to the back more. Sorry, when x is negative 2, y is 0, z is 0. Okay, sorry, that slice is more, I kind of made it in the y direction, it's in the x direction. So let me kind of fix this up a little bit. Okay. Come on. All right, there we go. So it kind of like slices to the negative x's there. Okay, so basically that shape is like this. There we go. Okay, and we can't describe that surface in terms of z. We can get the top okay. It's the sides, right? X squared plus y squared equals 1. It's not dependent on z at all. So if we wanted to do this, we'd have to like flip our axes, and rather than everything depending on z, maybe it depends on x or y. It's just going to get too tricky. Okay, we don't want to do this. We want to do this. Okay, so your divergence of f will be 4x cubed plus 0 plus 4xy squared. Okay, and then this volume, again, we're definitely going to use cylindrical coordinates, right? R is between 0 and 1. Theta is between 0 and 2 pi. And z is between 0 and x plus 2, or r cosine theta plus 2. Okay. So before we get too far here, let's go ahead and convert that divergence to polar. So we're going to have 4r cubed cosine cubed theta plus 4r cubed cosine theta sine squared theta. And we can use that same idea that we did in the previous problem. I can factor out a 4r cubed cosine theta, left with cosine squared theta plus sine squared theta, which is 1. Makes it easier. Okay. So let's do 0. I'm going to do 0 to 2 pi last. Then 0 to 1. I just prefer to integrate with respect to r before theta. I don't know. Personal preference. Okay. Then remember, we're going to have that extra r from converting to polar. So 4r to the 4th cosine theta. Okay. And then we've got dz, dr, d theta. All right. Almost done. Let me check, make sure I'm still recording. Yes. Okay. I was super happy when I realized that I had done the whole video and it hadn't recorded. That's the first time, actually. First time it had happened all semester. So I guess I can't complain too much. But anyways. All right, when I integrate with respect to z, that's it. We just add a z in there. So we're going to have r cosine theta plus 2 times 4r to the 4th cosine theta. 0 to 1, 0 to 2 pi, dr, d theta. Okay. We will distribute. So we'll have 4r to the 5th cosine squared theta plus 8r to the 4th cosine theta dr d theta. Okay, integrate with respect to r, and I'll have, let's see, 2/3 r to the 6th cosine squared theta plus 8/5 r to the 5th cosine theta. Evaluate from r equals 0 to r equals 1. So that's going to be pretty nice. So we'll have 2/3 cosine squared theta plus 8/5 cosine theta d theta. All right, we got a cosine squared, so we need to use our trig identity there. Okay, the 2's cancel. So I have a 1/3 minus, what did I just do? Did I mess something up? 1 minus sine 2 theta over 2. That's right, the 2's cancel out. 1/3. Okay. Over 3 plus 8/5 sine theta. Okay. I'm remembering back to the video that I just did, and I must have made a mistake in that other video. I had 2 sine 2 theta. Okay, but it is supposed to be 2/3. Yep, that's right. Oh, doesn't if it doesn't work out, I'll check. All right, 1/3 theta plus cosine 2 theta. The derivative of cosine of 2 theta would be sine 2 theta times 2. So I need to do a 1/6 there. Okay. And then plus 8/5. Oh, that should be cosine still. I was thinking ahead like I already integrated. Sine. Okay. From theta equals 0 to theta equals 2 pi. So I will have 2 pi over 3 plus 1/6 the cosine of 4 pi. So cosine 4 pi is 1. Plus 8/5 the sine of 2 pi, which is 0. Minus 0 plus 1/6 plus 0. So the 1/6 cancel out, and I get 2 pi over 3. Final answer. Last example of the semester. Give yourself a big pat on the back, and you did a nice job. Look, I'm still recording.